Alright, so Aiden, can you please mute yourself? Okay, so I'm going to start the recording now. Basically, this is my compulsory message to tell you guys that if you don't want to be recorded, your names are not being recorded, so just don't talk if you don't want to be recorded. Alright, so let's get started. Alright, so today we're going to be talking about thermo. So, like Ming said earlier, we're not just talking about thermostats or anything. We're talking about mainly thermodynamics as well as thermochemistry. So this is going to be pretty interesting, I think. So let's start with a quick overview of what we're doing today. Alright, so first we're going to start off by talking about thermodynamics, mainly the 4 laws of thermodynamics, the 0th through the 3rd. I thought it was pretty important because some of you guys, during trials, this came up and then it was not common. So we'll cover this today. The second topic we'll talk about today is thermochemistry. So thermochemistry is quite interesting because it relates a lot to thermodynamics, and it's one of the topics in chemistry that is very closely interrelated with physics. Next, we'll briefly gloss over energy and spontaneity, which is kind of important, especially when you want to tell whether a chemical reaction is favorable or not. And then next we'll try something new today. So we'll do a Kahoot, but kind of not really. So it won't be the traditional Kahoot you guys are used to. If you were here last year, we kind of did a quasi Kahoot that similar last year, and we'll try that again today. Depending on how much time we have, we'll try to get through all of it. Today's PowerPoint is pretty short to make some time for the Kahoot. Did you have a question?
By spontaneity, do you mean exploding?
Can you say that again?
By energy and spontaneity, do you mean the chance of explosion?
Oh, so what you're probably talking about is spontaneous combustion, which is a little bit different. It's not necessarily the chance of explosion. Yes, not in this case. It's basically we'll talk about this a little bit later, but it's kind of like whether or not a reaction will happen without special conditions or like energy input. So like I mentioned, we're going to do a kind of Kahoot, and finally we're going to have our normal matches for the day, like always. So let's get started. First, let's talk about what is thermodynamics. So thermodynamics is essentially thermo. You can see the root of thermo is heat or hot. Dynamics is just like movement or motion of bodies. So we're essentially going to study the movement of heat, energy specifically in the form of heat, and this will apply to chemistry as well. All right, so let's first talk about the fundamental basis for thermodynamics. So conservation of mass is very important here because, well, like some of you may know, if you were going to the quantum level, you would have conservation of mass and energy, but in this case, we're still staying in the Newtonian level. So we're going to stick with conservation of mass. So conservation of mass is really important here because a lot of times in thermodynamics, you deal with closed systems, meaning the systems you do, like no mass is going in, no mass is going out. Sometimes you'll put energy input in and work output out, but you won't actually change like the amount of mass in here. So that the mass remains the same is quite important. So next, let's start by talking about our 0th through 3rd laws, which are quite important. So a little bit of history behind this. We notice that we have 1, 2, 3, and then 0. So the 0th law was actually added after the 1st, 2nd, and 3rd, but they named it the 0th law because scientists thought that it was a more fundamental law than other laws. So that's why this one is called the 0th law. Alright, so the 0th law essentially concerns systems in equilibrium. And let's look at a diagram to see what it exactly tells us. So suppose we have 3 systems, system A, system B, and system C, right? What the 0th law of thermodynamics tells us is that if system A is in equilibrium with system B, and also in equilibrium with system C, that means systems B and C are in equilibrium. Now this is, if you can think of this as somewhat equality, right? If you're in math and you have A equals B and A equals C, then naturally it's transitive and B equals C. So this applies to thermodynamics as well. So this may seem somewhat intuitive, but it's important to state as a law because it can be variously applicable. So the first law of thermodynamics, however, is also very interesting. Basically, it's an adapted version of the law of conservation of energy for thermodynamics. So if you were to adapt conservation of energy for relating to heat and heat energy, this is what you get. So what does this say? It says that change in internal energy is equal to heat input minus work output. So heat energy input, essentially. So that means if I'm putting as much heat into a thing as work I'm getting out of it, then my internal energy is not changing. So what does this mean? Well, if you have a perpetual motion machine, this first law effectively disproves your perpetual motion machine. Because if you consider your perpetual motion machine to be a system, then it's impossible to forever get work output from it. Because we're assuming, of course, that we're not putting heat input into the system. And it's impossible to continue getting work output out of it because some heat energy is always wasted through friction or other non-conservative forces.
Um,
Go ahead.
can you please repeat what exactly does change in internal energy is equal to heat input minus work output?
So you can kind of think of it this way. Um, the amount of energy that changes in me is the amount I get in minus the amount I get out, right? So if I get in more than I put out, then my energy goes up, right? But if I get in less than I put out, then my energy goes down. It's essentially conservation of energy, right? So basically, energy cannot be created nor destroyed. The amount I get in must either go and stay in me or it must come out. So this is essentially in equation form. So the idea of the perpetual motion machine is to try to continuously create work without changing internal energy and without putting heat input. So if change in internal energy is 0 and heat input is 0, naturally you can solve for work, which must also be 0. Therefore, you cannot have a perpetual motion machine. So a really common example is one here. You guys will be taking a look at it in your extension. Essentially, going over it quickly, you can notice there are two types of balls here. One, well, two groups essentially. One where the balls are closest to the center, and one where balls are closest to the outside. Give me a chance to finish this real quick. So the balls on the outside are supposed to give more torque than the ones on the inside, but this ends up not being a perpetual motion machine, and you'll take a look at this in your extension. And then go ahead. No question?
And the slide didn't change.
You should be seeing kind of a wheel. Let me go back and go forwards again.
Yeah, I see the wheel. I saw the wheel.
Okay.
Okay, now it's there.
Okay. Yeah. So this is an example of a type of perpetual motion machine that people try to create, but it doesn't actually work. Heat loss due to friction still causes it to lose energy overall. Alright, so let's continue on to the next slide. So the next is, so first law of thermodynamics applies a number of principles that are really important in general in physics. The first one is conservation of energy, like I mentioned earlier. Assuming we're not going to the quantum level, energy is always conserved, especially at the macro classical level. So energy you put in is equal to energy you put out, assuming the internal energy doesn't change. So this also takes in the idea of internal energy and temperature. So we'll also approach this on a later slide, but this is the idea that energy of an object can be split into three parts. It can be split into kinetic energy, which is energy of movement, potential energy, which is like energy inside your gravitational due to forces essentially, and the final one is called internal energy, sometimes also called chemical potential energy, but internal energy is generally preferred if you like, because normal potential energy, such as spring potential energy, gravitational potential energy, etc., results from a force. So the chemical potential energy isn't really a force. That's why sometimes scientists like to label it as internal energy instead. Another applied principle is work. So this is the idea that work is essentially the ability, energy essentially is the ability to do work, right? So work, generally you can calculate it using a number of formulas. One of them is force times distance, and this is something you might see in your physics study in the future. And I think this is the last one. It's heat flow. So it concerns the idea of heat flowing in and out of a system. In this case, we relate heat flow to the internal energy of a system. Alright, so now let's talk about the second law of thermodynamics. So this is really simple, actually. Second law of thermodynamics just states that entropy increases in the universe. So what this means is that, in general, if you take the entire universe as a whole, the randomness of the universe always is increasing. Now, a funny story about this, actually, there was a question on the tryouts, the buzzer tryouts this year, where the question was, which law of thermodynamics states that entropy increases? Well, this is a little bit of a parenthesis.
Didn't everybody who attempted it get it entirely wrong?
That is funny, right? So three people guessed it, and there are four possible answers: 0, 1, 2, or 3, and nobody guessed the second law. So that's a little bit unfortunate. But now you'll remember, second law of thermodynamics states that entropy always increases. So what this means is that randomness is favorable. The universe wants things to be random because random has a lower energy state. Like I mentioned in previous chemistry PowerPoints, everybody is lazy. They want to be in the lowest energy state possible. When you're sleeping, you don't want to stand up. You want to lie down, right? Because essentially your potential energy there is lower, with regards to your lowest energy state at least. So you want randomness because randomness is lowest energy. This also relates to the irreversibility of natural processes. So in general, we can say, oh, a lot of processes are somewhat reversible, but in reality, in like the macro scale, for example, a star's supernova is not reversible. That's because of the extreme entropy difference. Basically, in general, most processes are not reversible. Say if I were to have a piece of paper, say this piece of paper I have right here, say you could, yes, go and recycle it and then turn it into another sheet of lined binder paper, but it wouldn't be the exact same. The molecules that were in it are not going to be the exact same molecules that were in it before in the same locations. So in general, in natural processes, it's not possible to reverse them. Alright, so a good example of entropy, which we'll revisit at the end of this PowerPoint, is this picture right here. So, say we have four molecules of gas in a container with a separation in here, right? So, just being really simple, how many total ways are there to put the four distinct molecules in either of these two containers? So, like, two possibilities are shown here. Does anybody want to answer?
2?
Not really. So this is two possibilities here. Not quite either. So how we want to approach this is with a purely math kind of perspective. So let's call this molecule 1, 2, 3, 4, right? So molecule 1 can either be in this box or in this first box or the second box. So it has two choices. Molecule 2 can also be either in the first or the second. So it has two choices. So if we take to the power of 4, we have 16 possible choices. But in reality, our molecules are identical. So why are we labeling it like this, right? So what I'm trying to say is, for all 1, 2, 3, 4 to be on one side, that's just one possible case out of 16. Whereas when we have 2 here and 2 here, well, this one could be 1 and 2, you don't know. This could be 1 and 3 as well, or 1 and 4. And this totals up to 6 possible cases where we have a 2 and 2 split, right? So this means that this configuration is 6 times as likely as this configuration. However, in real life, when we're talking about gases or liquids or whatever, we don't just have 4 molecules. We have on orders of 10 to the power of 30, not 10 to the power of 30, that's really large, but like 10 to the power of 25, etc. molecules, which is a lot of molecules. And therefore, the chances of all of them being on one side get lower and lower, and the chances of them being close to even, if not almost even, are much higher than not. That's why entropy favors things mixing together, and we'll have some examples of entropy increasing cases later on. So let's talk about the third law of thermodynamics. So the third law essentially states that the entropy of a system as temperature goes to absolute zero is constant. And why is that? Well, entropy essentially is randomness, right? And we may know from chemical theory before that when molecules and materials go to absolute zero, they're not moving, right? They've lost all vibrational kinetic energy, right? So if things aren't moving, how can that randomness change? It can't, right? So here's a question. Do you guys think that the entropy of a system when the temperature goes to zero should be zero, close to zero, or can it be any number? What do you guys think?
Zero?
Zero?
I'm pretty sure randomness, the value has to be zero. But doesn't the second law of thermodynamics say that entropy is always increasing?
Yes, it is, but
Yeah, that is
okay,
true.
let's clarify that. So yes, the second law does say that entropy is always increasing, but entropy, that's with regards to the entire universe, right? So if I'm putting energy, if I'm taking energy out of a system, say I have a bottle of liquid water and I want to freeze the water. Yes, the water's entropy is decreasing, like we'll talk about later, but the overall energy of the universe is increasing because the energy I'm taking out of the water is coming to the rest of the universe, and that's increasing the entropy. So, to be honest, all of you are essentially correct. It doesn't have to be zero. It can be a lot of different things. So it could be zero. It could be not close to zero, or like pretty large. It could be close to zero, and it could be zero. So let's talk about which ones are these, right? So not close to zero. Imagine if you have a piece of ice, right? And if you keep cooling it and cooling it and cooling it all the way down to absolute zero, it's still going to be ice. And the ice has a crystalline structure. So the materials with a crystalline structure, such as ice, other solid materials, not necessarily all solid materials, but some other solid materials, will have entropies that aren't very close to zero because the structure provides order, and that well, sorry, that's a little bit backwards. Sorry, it has a structure, therefore it's not necessarily in its lowest energy state. So although the randomness is pretty low because it's structured and it's not moving, it's not as low as possible when it could just be everything fell on the ground. So I guess an example of this would be like which one would have less entropy, like a cube that's like 3 by 3 by 3, or just a sheet on the ground. And I think that in this case it should be the sheet on the ground. Alright, so close to zero. Most materials are actually close to zero. And this is because sometimes materials can have multiple states with the lowest energy. So this means that overall I can't get to zero because of the different possible states. However, some materials do have only one lowest state, and this is when it's zero. So let's move a little bit faster so we have time for the code. Alright, so next let's talk about thermochemistry. Unfortunately, I didn't get a good picture for this, so it's just a white slide. Alright, so let's talk about chemical reactions first. So like I mentioned earlier, total energy is internal energy plus potential energy plus kinetic energy. So what chemical reactions do is that they can convert energy into internal, or it can convert internal energy into other energy. So this is essentially, if you think about in terms of chemical potential energy, you're essentially releasing that potential energy, or you're building up more potential energy. So we can classify chemical reactions into endothermic or exothermic. This is basically where either the system is giving away energy or it's taking in energy. In this case, when the system gives away energy, essentially, like for example a fire, when heat is coming out of it, this is exothermic. So exo pushes out energy, while endothermic takes in energy. Something that an example of this is maybe when ice melts. You have to put heat into it in order to melt the ice. So delta H is essentially describing the change in enthalpy, which is essentially similar to the change in internal energy of a system. So can somebody tell me what the sign of delta H is when we have an exothermic reaction?
It's positive.
That's a great guess.
What is that?
Noem, go ahead.
What is delta H?
So like I just mentioned, delta H is the change in internal energy, change in enthalpy. So notice that exothermic, you're giving away energy to the outside, right? And if you recall back to our
delta H is reduced.
Yes, delta H, well, not delta H is reduced, but internal energy is reduced. Thus, delta H is negative, right? So that was a great guess earlier. It's alright, this is not the easiest topic. So exothermic, you're giving away energy, therefore your internal energy is decreasing. However, endothermic is the opposite. You're taking in energy, so your internal increases and delta H is positive. Alright, so let's talk about bond energy. Like I mentioned before, bonds give off energy when formed. And this is because a bond is essentially a lower energy state than when it was by itself. So like if you have a hydrogen and a hydrogen, that's pretty high energy because they're repulsing and stuff. But when you bond them together into H2, it's a lower energy. Bonds also require energy to break. So by examining these bonds, how much we break and how much we form, we can essentially calculate the enthalpy change, right? So if we look at this diagram, suppose we have the reactants right here, and notice, say this is O2, for example, and this is CH4 and O2. Let's see what happens when we break all of these bonds, right? So if we break all the bonds, they turn into separated atoms, and this takes energy to do, right? So the energy level essentially goes up, energy expenditure. But then afterwards, these separated atoms form into different atoms. In this case, this looks like H2O and CO2. So when they form bonds, the energy is given off. So depending on how much energy is given off, you can tell whether a reaction is exothermic or endothermic. So one way of calculating is here. Basically, the simplified version is you just calculate how many bonds you broke and the energy of that, and how many bonds you formed and the energy of that. So if the amount of bonds you broke is greater than the amount of bonds you formed, that means you took in energy. Delta H is positive in this case, because you needed more energy to break than you gave off when you formed. However, when you broke less and formed more, your delta H is negative, and that's essentially an exothermic reaction. Alright, we're getting close to being done. So the next is a heat of formation. So heat of formation is essentially the amount of energy needed for a molecule to exist. So fun fact, this actually appeared on the Interlake High School chemistry screener too. Alright, so this is heat of formation essentially is the amount of energy difference from the standard state of a molecule. And you can kind of think of it this way. So the standard state of a molecule never changes even throughout the reaction. So suppose we have, this is the, what's it called? This is the photosynthesis. This is the, cellular respiration. This is the cellular respiration reaction. So since mass is not destroyed, matter cannot be created nor destroyed, the elements we have on the left side is the same as the elements on the right side. So these standard states listed here, I won't go too much into detail about what exactly the standard state is, but these standard states are the same. So therefore, essentially the basis is the same. However, we can calculate the heat of formation of C6H12O6 as well as O2, right? And we can also calculate the heat of formation of 6CO2, 6H2O. And the difference of the heat of formation is essentially, so the difference between this long one and this long one is essentially the enthalpy change in the reaction. So let's see kind of how it works here. So what we want to calculate is the overall change in energy, right? So like I mentioned before, the overall energy is essentially you can calculate by subtracting the energy of the reactants from the energy of the products, right? Because if the product's energy is higher, that means you have to put energy into it. But if the products are lower, then you gave off energy. So we can essentially add and subtract standard state to get the same equation. So this is equal to this. Notice that the standard state is added here if you switch the sign, and standard state is subtracted here. So these cancel just to give this. And what this gives us is products minus standard state. Like I mentioned earlier, this is a heat of formation, and this is a heat of formation as well, of the reactants in this case. So what this equation, this really complicated equation is, I don't know why they overcomplicate this, but what this equation is essentially saying is that the enthalpy change is equal to the heat of formation of the products minus the heat of formation of the reactants. This is just a different way to write this. So this is very close to the end. Hess's law is essentially, basically you're saying when you have multiple reactions, you can literally just add the enthalpy changes to find the overall enthalpy change. So here's an example. Suppose we have two reactions in a row. The first energy change takes the products and changes them into reactants. So therefore, the energy change is products minus reactants. The second reaction suppose this takes the new reactants and then takes the reactants and makes them into new reactants through another energy change. Now let's see what happens when we add these two. When we add these two, the reactants, the negative reactants here and the positive reactants cancel. So the end reactants is just products minus new reactants. And notice, in the end, what we want to find is the energy change, the products minus new reactants. So that means that when we add these two equations, we find that the final energy change is equal to products minus new reactants is equal to the first energy change times plus the second energy change. Therefore, we can just add the energy changes to find the overall energy change. Alright, and finally, entropy randomness, like we talked about earlier. Random is favorable, random is good. We want to compare some stuff. So I'm going to give a bunch of comparisons, and I want you guys to try to see which one is more random than the other. So the very first example is water versus ice. So what do you guys think is more random?
Water.
Water, right.
Water.
Water is the liquid form. Ice is the solid form of water, is a better way to say it, right? So liquids in general have a higher entropy than solids. So in this case, water is higher. What about water and steam? What do you guys think?
Steam, definitely.
So by the same token, steam has higher energy than water. Steam is the gaseous form of water, therefore it has higher entropy. Now we're going to get a little bit more tricky. So what if we have 1 liter of nitrogen versus 2 liters of nitrogen? Assuming we have the same amount of nitrogen, it's just a bigger volume. What do you guys think has more randomness?
It depends on the container.
Nitrogen.
1 liter would have more.
Liters.
I thought it was 2 liters.
2 liters actually has more, because the way you can think of this is that in this first case, you have 1 liter of nitrogen and 1 liter of vacuum, where in this case, you have 2 liters of nitrogen. So this, let's skip this next one for a second and go to the next slide. This is essentially another version of this case, right? So what has more randomness? Everything in 1 or split across 2? And the answer in this case is splitting across 2. Therefore, the answer in this case is 2 liters of nitrogen has more randomness. Alright, and our final comparison is what do you think has more randomness? 1 liter of nitrogen by itself, 1 liter of 1 liter of hydrogen together, or put mixing them together into a 2 liter bottle. Which one do you guys think?
Mixing.
Yes, mixing is more. And this is kind of intuitive, because when you mix things together, you think it should become more random, and it does, and this is the case here. And this is, again, our diagram from before. Today, for your additional topics for studying your extension, we'll look into the Gibbs free energy, perpetual motion, as well as specific heat and heat capacity, which I didn't get to today. Yeah, so I'm going to stop recording now, and we'll move on to our next activity, which is the Kahoot. So, yay.